freshwater, and within freshwater there is some other parts of the water, like the freshwater and also the soil moisture, groundwater, and also the deep groundwater. And within that, we have some surface water percentage, which include the glaciers and ice as well. And within that, we have some other percentages. So just make the whole story short, that overall water is very important in our life, because we have a different distribution of water, and we need to, considering this water as a resource, we need to utilize it in a proper way, so that we can have it for the long time, for our next generations as well. There are different parts that we can monitoring, or we can monitor, or we can how we can, with the passage of time, we can make a policy or some other instruction for the water. So for that purpose, we have some in situ based instrument, which are giving us some outputs regarding the either the quality of water, either the overall percentage or depth of water, or some other other parts of that, so that how we can calculate the water for that specific area. So that is one of the part, and another is the remotely measurement, which are also important for us, that how we can remotely measure the groundwater or the surface water or its quality. So basically, I have divided that my presentation part to the two parts. One is the one we will be talking about the surface water, and another is it's about the ocean and also coastal water. So application of remote sensing in the surface water, which is the land, and also the ocean and also the coastal areas, application in remote sensing. So in situ measurement of various hydrological parameters, like we can see here, precipitation, water depth, temperature, salinity, it's possible for the specific location. If we talk about the in situ measurement, for example, I am sitting in the International Islamic University and I am measuring something, so that would be specifically about the location. But if we want to talk about the whole area, so that is that you cannot based on that one location, that you can promote on the basis of one location, you can have the whole area of Islamabad, you can consider it. That is not easy, and that is not possible at all. So those type of difficulty for the in situ measurement, we can handle it with the remote sensing based data. So that is some of the locations we have taken from California. They have some point-based location where they have the 152 continuous recording stream flow gauges. But the thing is that those all monitoring stations, the developed countries, they can do at some points. But if we talk about the developing countries, they don't have that much capacity to make a lot of in situ measurement, because that is also need to be monitored and also costly, and at the other end, it need the human resource as well. So considering that type of problems, we need to go for the remote sensing measurement. May provide especially continuous and extensive information about the variety of hydrological variables, which include those type of applications we can consider using the remote sensing and GIS. We can get the help from those type of applications, like water surface areas like streams, river, lake, ocean, etc. We can consider we can make its boundaries, and also it's how much it's increasing with the passage of time, or how much it's either decreasing or either increasing. So those type of monitoring of groundwater is important, and also it can be done by the remote sensing data. If we talk about the in situ data at the moment, so it cannot be done using the in situ data, because that is for the specific location, but we need to consider the overall area, that either, for example, the streams or rivers or lake or even ocean, that is the tidal waves are increasing or decreasing. So that is one of the part, and the another is the water constituent. So that is also very important, that what type or what type of minerals you are calculating, either if they are organic and inorganic, and different other parts which we will be discussing with in our slides as well. And also the water depth bathymetry, that is called, that we can also consider it the water depth. That is basically the sonar data is using, that is relevant to the radar data. So basically, within that, the sonar data is using for the water depth and water surface temperature and snow surface temperature, and also the snow water equivalent and ice surface, and then we have some precipitation and also the water vapor. So those all are the application which we can consider for the application of remote sensing and GIS for the groundwater resources, because those all are the groundwater resources. So we can consider different data from the remote sensing and then process it in the different GIS softwares related to that. This is basically the overall pattern for the land surface. We will be doing some exercise in that as well. So we are actually considering the special part of that one, that how we can consider the special streams of the data, and also how it can be helpful for the overall channels, that if we want to use it for the agriculture purpose or some long-term area, so how we can calculate the stream flow for the overall area if we have a big area where we cannot use the, it's not easy to use some monitoring station, and also we need to find the flow of the area. So that is one of the way that how we can step by step go toward the drainage and also the watershed management. That is called overall, the step is watershed management and delineation of watershed. So that is basically used for the step of we can use it for the surface water, and also further we can establish some specific outputs from that one, so that we can use it for the next process of the delineation, and also for example, if we use it for the agriculture or some planning to mitigate the flash floods, and also some other application can be used. So that is basically whenever we have digital orthophotograph, so we can use it. We can use this one, like we can have a rainfall response, and also a terrain surface, and then channels, and then hydrography, and then we have some drainage areas. So that is basically the overall process of for the stream sediment stream flow, and we can find the stream flow for that area as well. This is basically how things working for the data model, that if we have some rainfall here, so how that drop can be followed by different flow, and then it will be from the stream toward river and river toward the ocean. So how those type of flow will be working, like this is, for example, we have some mountainous area, so we can here find some slope using the digital elevation model. That is basically give us the height of any area. It's up to some pixel, like the 30-meter resolution. So basically, I hope you got about the resolution of the pixel. So basically, whenever we are using that specific location or specific topography for the data, so we use the digital elevation model for the area to make the overall groundwater watershed management. So for the watershed management, we need to use the digital elevation model, and also some other application can be used to make the watershed for the overall area. That is the integrating the data inventory using the behavior model. So basically, whenever we use some that, for example, we talking about that specific graph, which is from the by precipitation. So how we can calculate and how its relationship with the overall area. So that can be used by step process. That, for example, if we have a drop here, so how it has a relationship towards this one. So the thing is that if the flow is in this way, so of course that drop can you hear me? Uh, Hello, can you hear?
Yes, sir.
Can you get? Okay, sorry. I don't know why it's again disconnecting, but anyhow, let's continue. So that was the overall process for the step-by-step flow of surface water, which is going toward the ocean, and that is basically whenever we talk about the relationship between the object linked by the tracing path of the water movement. So that is basically that how one, for example, if we talk about one drop is connected toward the stream and then connected toward the river and then connected toward the ocean. So how its one drop is flowing, so that we can calculate using the watershed management. So that is basically seen on the using the digital division model. We can calculate that one, which we will be doing with the exercise as well. So basically, a geodatabase model that is basically collecting the feature data set like the workspace and collection of feature classes. Uh, that is basically a step-by-step process which we will be doing in our model of the whenever we using the model for the groundwater delineation. So that will be step-by-step process as well. So this is basically hydrological components which we will be using in our experiment and how it's working overall. So that is very important to know. So that whenever we have our drainage system, so that is basically the water is flowing from one point and that is connected to another point. That is important. So first of all, we like if we talk about here, from here to here or from here to here. So that is very important that, for example, if we talk about hydrography, so that water, that area is connected from this one toward this one. So how we can say that this point have the watershed catchment area, including this whole area, because whenever if some rain is here flowing, so that water flow will be connected to this stream, and then this stream will be connected to the main stream, and then going toward the river, and then it will be go toward the ocean. So that is the basically mm, the overall area calculation, that how it's basically calculating the stream flow and how it catchment area can be calculated using a different using the detailed emission model by including some other parameters as well. So that is basically whenever we have, for example, those points like those green points, so we can find the overall. For example, if I put some point here and want to know the catchment area of this till this point, so that will be basically if the stream coming toward this one till this area, so that will be calculated at the back from the back side like this one, and then it will be calculated the overall area. So that is the whole process we are talking about today, and we will be talk about it in the explanation in the next slides as well. So basically, that currently we are talking about surface water. So that is water delineation as one of the main part of the surface water. Whenever you talk about the overall things regarding rega regarding the flow of the water, that how water is flowing from one area to another. So that is important. So currently, like we can see here, the sun area has a blue catchment channel system. So that is basically explained here. That, for example, if we don't have water in the in some winter season. So, for example, we don't have a water at this area. So, if in the summer we have a lot of water because mostly the glacier is melting, and also we have some monsoon rainfall. So that basically consider that how much catchment area or how much channels are uh, basically connected to one another, that it's going from one place to another, and then it's the speed of flow and also the discharge values are very important. Mostly in different countries, we have some type of the flow and the gauge station or discharge station that show basically that show us the overall area and also the flow of the flow of the overall steps, that how the surface water is either increasing in the flow or either decreasing. So that is one of the important step toward the to overall situation, that if we have, for example, if we have the water flow catchment at this area, so that area will calculate it under the path of this whole step. Because if we have some rainfall here, so that is basically coming toward and then it include toward this one. So that is input. That input is given toward here. So that is basically connected from one place to another. And then we can see here the time series of flow. So that it might be like I talk about the summer and winter. So that in summer we have Sorry for the interruption. There is some issues regarding, I think, some internet issues. So that's why it's problematic and with the passage of time. So anyhow, we can continue with this with the water flow. Okay. So this is basically the catchment area for that specific location. And we can see here the overall. We can see here the overall. Can you hear me?
The voice is gone now. At the start, we could hear you.
Is it okay now?
Yes, it's better.
Okay. Sorry for the interruption. I don't know why internet here is making some issues again and again, but anyhow, we can continue with the catchment drainage lines and drainage points at this specific locations. We can find the different catchment area. So we can, like in last slide, we have seen that we have some different catchment areas here. So we can, here we can see that if we have the multiple streams are connecting from one place to another, so that single stream have its own catchment area. So basically, if we talk about this single stream, that catchment area is connected from this area to this area. So that catchment area is basically this one. So same is the way that every area, every stream has some catchment area. So that is basically whenever we are explaining, we are developing some models, so that catchment area can help us at how much every stream have its own areas. So that is basically like here we can see if we put it a single point here and we can find the catchment area of that point as well. Now coming toward the scale representation of drainage system. So basically, whenever we have some basin and that single basin is connecting with some other basin, that is watershed, and then we have some catchment area and data division. So basically, from the one by one step, we are getting the first of all we have some digital division model, land surface terrain grid cells, and then we have some catchments subdivisions of the basin into elementary drainage areas by physical rules. We have some specific rules for that one, that how, for example, that catchment will be described. Like if we see here, then that is single stream catchment. But if we talk about the mega area, for example, the flow of this area is here. So if we want to know the overall river flow or river catchment areas, that is basically including the whole area as one. But if we want to find the catchment area of every single stream, so that is basically a different thing. And then we have some watershed. So now, whenever we have some power point at one location, so then we can find the watershed of that specific area, and how much its watershed, its area is calculating from one place to and covering the whole place for whole. For example, if we say that from one stream that water is coming, so that whole area is connected with this single stream, that how much water will be flow from that whole area if there is some precipitation or some specific some other occurrence of rainfall or flash flood. And then we have some basin that is basically the drainage area of water resource management. That basically shows that if we have a single, like if we talk about the overall basin of the area, so we can see here that this is the single flow. So we have a different input toward that flow, but we cannot see any multiple flow of this whole area. So that whole area have a single flow. So the single flow basically show the overall uh, area inputs from that specific locations. Like we can might be this is the mountainous area, and also we have some plain area, but the downward area basically show the basin, and that is basically maybe a river or something like that. So like if we talk about here, so this is basically the flow of the whole basin. We talk about that one. So that is basically the basin, that including the whole area and different streams for the area. This is the hydro network through and that is one of the Sion Lake. That shows that how much the water is flowing if we have some, for example, water reservoir in the area. So that is basically shows that how much the reservoir is calculating its have flow from the different locations, and also it's dumping here. So that is storage capacity of the water is also important to be considered, and that can also be considered by remote sensing data. So basically, those all things we are discussing is basically need to know that this all those all are the application of remote sensing and GIS. So so whenever we talk about stream flow or the watershed management, or even the next will be the groundwater and some ocean and something. So that all is basically connected toward the water, toward the remote sensing and GIS applications. So that's why we are basically talking about the overall groundwater system and management, but that whole step and whole applications which we have discussed before as well. So that is including in the groundwater management, and also using the remote sensing and GIS data. This is one of another example, the catchment subdivision divided at the watershed outlet. Basically, outlet is whenever we talk about the outlet, that shows the overall area that which one, for example, this area have input from here as well. So that is first outlet of the area. Okay. So then this is coming toward input, but this area have its own catchment area as well. It doesn't mean that the same water is flowing from this area to this area. That is basically whenever we have different catchment area from different locations, so that is basically considering and making it individual, that this, okay, this catchment area, for example, this catchment area has its own location, but this one is totally independent from this one, because there if we have some for example precipitation here, so that will not flow toward this one, but that will flow toward this area, right? So that is basically whenever we talk about the flow and the precipitation, so that includes from different waves, from different streams toward this one. So that is basic step-by-step process, and also including multiple catchment areas for the watershed management. And then at the end, we have this one, which is from the different areas as well. Now, the water quality modeling, that is basically the modeling of water quality. There are different source of the water quality which we are modeling for different area. But the thing is that whenever we talk about the single location, So that is basically problematic because whenever whenever we are talking about point location, that is basically specifically connected to one area or one point, but it's not connected to multiple different points locations. So that is uh, important to be relatively easy to control and regulate if we have pollutant or some point from one specific discharge. For example, if I talk about the single industry output of water, so that will be very easy to identify that. Okay, this is the product or this is the outcome of this industry. So that is more polluted or even less polluted. So we can take mitigation according to that. But if we have the diffuse data set nature of water, so that is very tough because we have a different inputs from the different sources. So that is important, and that is also very need to be controlled. That how the pollutant of non-point area source pollution is considered. So how we can consider that one, that pollutants are coming from the range of sources that are diffused in nature. It's difficult to control and regulate because it's indirect. Because the thing is that it's different sources. So different sources are involved. It's diffused because like we have taken the example of industrial water, but if we have a residential area connected with the industrial input, so how we can differentiate between both area? So, flow accumulation of pollutant is a result of this widespread activities in urban and rural areas. So that is one of the way that how the flow accumulation of pollutant can result in can be modified and also can be differentiated between two areas. The major non-point source of pollutant are sediment, nutrients, and acid and salts. That basically those all the inputs might be from the industry, and even some of them are can be from the residential area because some of the things are using within the daily base at the homes as well. So that is important. So the major source are the like we can see here the residential area like construction and building site of mining operations and those type of logging operations and then stream bank erosion and then multiple like there are different ways that how those non-point source of pollutant can be generated, and that is very important and also very difficult to be identified by like we have multiple parts like runoff, urban runoff, irrigated lands. One point I would like to include here is that the irrigation land is very important because we have some issues regarding the irrigations and multiple the the organization, the government organization has ban on all the water because those some of the water is coming from the different industrial zones. So that is basically not good for the plants. So they have some ban on that specific area, but the river water we can utilize for the irrigated land as well. So now coming to the non-point source pollution, it's a complex problem like we discussed already, but the best addressed by the integrating in situ data, GIS and remote sensing, and then modeling and interdisciplinary collaboration. So now coming toward the point that basically the issues we discussed during the last two or three slides in non-point source of pollution that can be addressed, those issues can be addressed by some in situ data, GIS and remote sensing data, and then we can model it, and then we have some interdisciplinary collaboration like industrial areas, some resource person from that area, residential area, and also some other experts can help to make the differentiate and also to see the source of input from that specific location. Now, some factor to include in the water quality model is topography. As we discussed about before that, topography is one of the important factor for whenever we are talking about the water flow or the watershed management. So that is one of the important and very and very you can say this slope and slope shape and aspect and those type of multiple factors variables are very important to be considered during that topography. So whenever we talk about the water quality or modeling of water quality for example, one stream or one area, one region. So topography of that specific area is very important. So digital elevation model basically give us the topography of the area. Second one is the land use, and that is basically industrial and residential area. And also we have the land cover, which is the forest and grassland and water as well. So those type of inputs are important for us to be utilized for the modeling of groundwater quality. So that, and then we have roughness coefficient, meaning roughness coefficient, which is the flow velocity of water, and we have some curve number, and then we have storm data. Storm energy intensity, storm duration, and total storm rainfall and rainfall temperature concentration etc. is important. So those type of inputs are very important whenever we are calculating or we are modeling the water qualities. So those all the parts are key parts of the water quality modeling, and then we can identify some issues and also the non-point pollutant as well. Water surface temperature, we can calculate the water surface temperature basically whenever we are talking about thermal infrared remote sensing, which I hope you have studied in the last lecture of remote sensing. So that is basically thermal infrared remote sensing useful to assess the surface temperature during the day and at the night. That is basically the calculating the surface temperature of the area and day and night all the time. The problem with the water bodies as opposed to the land surfaces. Basically, whenever we talk about energy transfer by means of convection, it is mixing relatively uniform water surface temperature and also uh, high thermal inertia and all the water vapor relatively cooler than the land during the day. So basically, those type of information are very important whenever we talk about the thermal infrared, and we considering the thermal infrared for our whole area. So that is very important for us that how we can consider uh, that specific area for the mapping of using remote sensing data, and also uh, to consider the surface temperature of the water, how it can be, how it is increasing or how it's decreasing. So that is important. That is, we can see the day-night TIR, that is thermal infrared image of Atlanta. So we can see here the water at the daytime it's showing the black output, but at the night time it's giving us the output of white. So that is basically the surface temperature increasing and decreasing at the day and night time shows us in a very better way that how it's increasing and how it's decreasing day to night. Thermal infrared remote sensing, okay for the water surface temperature measurement, but it's not okay whenever we are talking about the subsurface temperature measurement. Because mostly, if we talk about the remote sensing, so remote sensing is mostly always not, but in some cases we have some subsurface up to few meter. But mostly in the optical remote sensing, we are always talking about the surface of the earth. Either it's a water, either it's a land, but it's always talking about the surface. But in some cases, we have some, for example, the radar data, which penetrate up to 1 or 2 meters. So that can be help us to find up to some few meters, not more than that. So two important thermal infrared sensors, both on NOAA, that is advanced very high resolution radiometer, and that the another one is geostationary operational environmental satellite, and that is basically used frequently to obtain the sea surface temperature measurement over oceanic surface at the 1 by 1 kilometer resolution. Basically, those all type of satellites which are giving us like if we talk about AVHRR, so those type of high number of satellites, this resolution is very close because they are working on the long area. So that is basically if we talk about the very high resolution, so that is not possible because they are covering the whole Earth's surface within short time. This is basically the sea surface temperature for the area, EVHRR, derived SST map in February 1993. That is basically collected from one of the report, which was generated by the USGS. And then we have at the August, the situation is different because we can see here at some temperature is up to 34 centigrade, which is very high at the surface of water. But if we talk about that one, the Feb, that is also almost somewhere same at the equatorial part of the Earth. So that is where basically the equator, at the equator stage, the area have a very high temperature. But if we go toward the polar region, Uh, Sorry for the interruption. So right now, I was just about to go in for the question answer session, but unfortunately it was disconnected. So now we can have some small question answer session because time is going on, so we need to cover a lot of things. But if you have some question, I think it would be better if you can write it in the chat. So at the end of the session, we can accommodate that. Is it okay? Okay, so we are going toward some marine applications for the water resource management. So that is basically chlorophyll concentration, productivity, carbon cycling, and water clarity and suspended sediments. Uh, uh, Also the ocean colors, fisheries management, and also the currents and rescue and deep sea dredging. So that is basically, I hope you can hear me. Uh, Can someone please respond so that you can hear me? Can you hear me? Okay, okay. Um, so some of the marine applications, as we discussed in the start of the presentation, that we will be discussing the two parts. So one is the surface water, and also the another one is the ocean or the coastline area. So that also I have included some groundwater part as well in the next one of the case study. So we will be trying to do it as soon as possible, because we have the time limitation, and just because of this issues of disconnection, so we don't have time. So basically, we are going toward the those are the different applications which we will be discussing. The ocean chlorophyll concentration, that is basically chlorophyll is used by the plant uh, and high light energy, which then derive photosynthesis. So basically, in the different research center and also in the related people, researcher to the water or water issues. So they are basically calculating the chlorophyll using remote sensing data. So that is uh, very best and very optimum way for the mapping of chlorophyll concentration in the area. Some of the paper are also published in my lab where I was studying. So in multiple people are working on that one. So amount of chlorophyll related to of the photosynthesis. So ocean productivity and carbon cycling, and also the ocean ecology, that is food web and fisheries. Can we estimate the amount of chlorophyll in oceans using the spectral data and models? That is basically one of the small example of upwelling of the coast of California, that how the area is calculating, how the area is land is grabbing by the ocean. So the upwelling of ocean is basically entering to the land surface, right? So whenever it's covering the land surface, it's mean that the ocean is increasing, and it might be a case of intrusion of water as well. So whenever the surface, the ocean water is intruding into the groundwater, so that is basically causing some issues as well in the area. The spectral properties of ocean, basically, the photoplankton spectral reflectance was similar to that land plant in the visible part of the spectrum. Basically, uh, different spectrums, different areas have a different spectral reflectance. But as we can see here, the land plant in the visible part of the spectrum have a same spectral reflectance as it's in the photoplankton. So the chlorophyll reflects a more green visible than the blue or red. So that means that the chlorophyll reflectance is more green visible than the blue or red, right? So within the green band, we can find the chlorophyll concentration in a more deeply or more explicitly. Can also measure the amount of fluorines with some sensors. Like MODIS is one of the sensor that is also have a special resolution of 250 kilometer. So that also can use for the overall the surface water, ocean movement, and also some other type of data can be calculated using MODIS data. So those type of big data set can be used for the uh, multiple changes of the area. So uh, those lights are almost all absorbed by the water and not a strong part of the ocean. That is important, that infrared lights almost all absorbed by the water and not strong part of the ocean. So that is basically that whenever you have an infrared part, infrared light rays that is absorbed by the water and not a strong part of the ocean, where we have a very strong plankton signature, there will be some lower observance of the of the IR rays as compared to another. That is basically, we can see here the wavelength uh, of the area, that how NIR wave has a decreasing percentage of reflectance toward this one, and but in the visible we have a very high spectral reflectance like 1.5 to even up to 2.7 or 2.8. So that basically shows that here if we have a clear water, so it will be decrease temporarily, but if we have the another one, that shows us the very high variation with the passage of wavelength in the nanometer, and also the percentage of reflectance within the area. This is one of the red tide of coast of Florida with the sea vibes, chlorophyll, and modest fluorescence. That basically in the different studies they have used the models for the chlorophyll estimation, and also they have find that if we have a high chlorophyll uh, concentration in the area, mostly the study says that the fisheries will be higher in that specific area. So that is one of the part that we need to study the chlorophyll concentration in the ocean, and also in the store in the reservoir, small reservoir as well. So that is important to be identified, and also to be notified that those types of important studies can be considered using the remote sensing based data. Um, if we talk about the overall remote sensing mission, remote sensing data, so that can be also help us in the water resources. There are different parts uh, like currently we are continuously talking about the ocean and also coastline area. In the next few slides, we will be talking about the fisheries as well. So that is important to know that how there is how some of the area are uh, connected with the ocean, and also it's giving us some productive output. So that calculation can be done using the remote sensing data, because that is very big area. So we cannot calculate, or we cannot do the monitoring area. If, for example, if I'm talking about this whole region, so here we can see the red tide. So the red tide means that there is a high concentration of the sea waves in the modus florona. So that means that it cannot be identified using the monitoring station, because we can see there is a high variation. So that type of studies can only be done by remote sensing. So here we can see a high variation within the area, and here it's very high variation. So that type of studies can be done using the remote sensing data only, but not with the in situ data. Yes, in situ data can help us to utilize our overall nature, our overall modify our results, but it cannot be used in the in all the areas. But remote sensing can help us to specially find the special variation. Here you can see very high special variation. This is the highest point, which is the 40. So in some point it's 40, and then it's somewhere uh, at 15 or 20, and then even 2 or 3, and then green, and then 0.04, which is extremely low, right? So that is basically show us the special variation um, of the, for example, chlorophyll concentration, or of the modus Florence. This is the red tide in California. So we can see here the identification of the ocean. We can identify it from the remote sensing image as well with the passage of time. Now, Mm. So, coming back to the point, oceans are net sink of carbon, remove some carbon from the atmosphere each year, but less than enter to the atmosphere. So that is basically shows that how it can be identified using the remote sensing data. It can be identified easily that uh, the net sink of the carbon removes some carbon from the atmosphere each year. So basically coming to the global carbon cycle, so that is basically input and output of the carbon. So we can see here the carbon outcome is 332 and carbon input is 334. So that shows that how the carbon is coming in and going out from the overall area. Water clarity and suspended sediment open the ocean water nearly sediment free, perfectly clear. It can be shown near shore water pools variables and sediment load and more turbidity. Basically, turbidity of the water coincide with the more productive part of the ocean near the shore due to input of the sediment or rivers. This is basically one of the example of turbidity near the delta in the nearshore uh, area where we have the high turbidity in the area. So spectral properties of turbidity water. Turbidity water are more reflective than the clean water. Peak in the spectral response depend on the amount of sediment, depth profile of sediment, and types of sediment mineralogy. Basically, turbidity can be a temporal phenomena, sediment input by the river after the floods, straight, and hurricanes as well. This is one of the examples. It's shown in the different uh, spectral response of every area in the specific location. So we can see here that how this is the wavelength and this is the reflectance in percentage. So how the high reflectance can be identified with the different water particles in the area. Now coming to the fisheries, fisheries have its own importance in a specific location. Like I have already discussed about one of the part that ocean fisheries are most productive where ocean productivity is high. So now the thing is that high chlorophyll content related to high productivity. So now, as I have discussed in the last part of chlorophyll concentration, so one of the study is conducted that they have shown that the chlorophyll A concentration shows that attraction of high fisheries in the area, but too much productivity or harmful blooms, red tides can be harm the fishes. That is one of the part that very high productivity of chlorophyll concentration can also affect the fisheries, which is, for example, the red tide can become. So the ocean currents, climate change, the nutrient inputs from the land, etc., affect the fisheries. Pollutions pollution can harm the fisheries, especially near shore. Now, the thing is that wherever we have some industrial inputs or some oil offshore, so that there the fisheries will be affected by the area as well. All these things can be monitored with the remote sensing and other geospatial tools. So those type of all the studies can be done using remote sensing and other GIS geospatial information that is basically location based and also the spatial variant of the information. This is basically one of the state of the world stock in 2004, recovering depleted, overexploited, and fully exploited moderately. And here we can see the world marine catch millions of tons by the major marine fisheries area. So this is basically the Pacific Southeast and Pacific Northwest. So we can see the high number of fisheries are in the Pacific Ocean, south or north part of the Pacific Ocean, and also third one is the Pacific West Central. So that shows that the Pacific region have a very high amount of uh, fisheries in the specific ocean area. And the lowest is about the polar region. Of course, there will be a very low, and the Atlantic Eastern Central as well. This is the global fisheries um, from this overall website. We have this one. So we can see here the overall pattern of the fisheries as well. Satellite for the marine remote sensing. Those are some satellites which are using for the study of marine remote sensing, flies in the orb view platform, and then they're designed to monitor the ocean color. And also like MODIS, I have discussed about it. So MODIS is on the Aqua platform, and then they have some models been designed to for the ocean of remote sensing. So that is basically the instrument which are using for the models. And also coastal application of optical remote sensing, that is coastal erosion monitoring, the hurricane damage assessment, and also the estuarine ecology, coastal geomorphology, coastal ecology, and human impacts. So now multiple coastal monitoring tools are there, like natural hazard, climate, weather, and also ecosystem and living resources and the US economy. So that is basically, it consists of both the national backbone and regional coastal ocean observing system. Uh, Now coming toward one of the case study, that is basically the uh, it's Chesapeake Bay is the largest in the US, important fishery and fish cobs and homard. So that is basically very populated coastal zones where vulnerability to erosion and sea level rise hurricane. Many issues are common in the coastline zones globally. We can see here the remote sensing in the Check Bay, airborne and satellite imagery used to monitor the chlorophyll concentration, monitor the sediment load. Like we can see here, all the sediments, all the application of remote sensing has been used in this case study. So this is one of the special variation of seasonal variability in the area, the chlorophyll concentration within the storage area reservoir. This is the hurricane in the area which is calculated by the remote sensing, and pre and post Istanbul flights in September 2003. And this is basically the overall step-by-step process for the regional algorithms and also the hyperspectral model, and then photosynthesis, and then leaf area index as a function of depth. So then bathymetry, and then also we have a mapping of the area that support the seagrass growth. This is a Check Bay ecosystem monitoring and prediction, and then annual integrated assessment of the tools, decision rationalize and needed. Now coming toward the another case study, basically my own case study which I have developed. In this case study, we have some objective of the GRACE-based data. GRACE is basically the um, GRACE is basically used for the GWS special mapping, time series groundwater, and also the depletion of groundwater. So basically, GWS correlation with the TRM, that is trim data, tropical rainfall mission, is basically used for the precipitation calculation in the area. And then we have the estimation of depth to the groundwater level from the GIS as well. This is the study area, the whole South Asia region, Pakistan, Afghanistan, India, and also the Bangladesh. So 4 countries we have taken for that specific study. And then we have the India is the most affected country from the groundwater extraction for the agricultural purposes and most affected state of the groundwater. So basically, data set we have used for that study is the remote sensing data has been taken to analyze the groundwater change from the India and Pakistan. So basically, Grace is using the basically the um, gravitational wave, that is gravity of the effect, and that basically give us the overall calculation of the groundwater. Uh, from the first of all, it's giving us the terrestrial water component, and then it's giving the after that we have some other parameters that are calculating one by one process, so that gives us the calculation of the groundwater and also the water subsurface water anomalies. So basically, the surface temperature is basically used by the different hydrological model like soil moisture and also the snow water content and canopy water content. So those type of content will be detected from the surface water, that is TWS, that is terrestrial water storage. So after that we will have some water content of groundwater, that is GWS, groundwater storage anomaly. So the another one is Grace and Gildas data. Uh, like we discussed about the gravity data, it's gravity recovery and climate experiment. It's available from 2003 to 2000. Basically, it's available from 2002, but in this study we have used from 2003 to present with the collaboration. It's this data is published by the Center for Space Research at the University of Austria, uh, and NASA, and also the German Research Center for Geoscience. And also the GRACE is using for the seasonal and annual groundwater change, store groundwater, ice and snow can be quantified by it. And then the GILDAS data is freely available for the soil moisture, snow water equivalent, and also the canopy water storage. And basically the TRIM data, that is the tropical rainfall measurement mission, that is the satellite uh, for the overall study. This includes the trim precipitation data, the GRACE TWS data, the GILDAS data, and also the groundwater monitoring data. Basically, and then afterward, we have changed the temporal well data, and also the canopy water storage, snow water equivalent, and also the soil moisture was used. And then we have some time series analysis of the GWS, groundwater storage for the affected area location, and also the monthly GWS spatial temporal mapping. So after all, we have some trend analysis and also the validation of trace-based GWS anomaly with the groundwater monitoring stations data. This is basically the GWS delta and how it's working. That is basically the terrestrial water storage, groundwater, the snow water equivalent, and also the soil moisture and groundwater, canopy water storage. Now here, how we can groundwater develop the groundwater storage mapping, that is for the time series analysis. So that here we have used the groundwater storage and then terrestrial water minus on the whole other subjects. The trend analysis show the overall annual pattern of the data. So trend, seasonality, and randomness. Depth of groundwater level estimation and prediction approach. This is we have used the approach for the depth to groundwater level estimation. Here we have a monthly depth to groundwater level estimation. The GRACE-based GWSB has been used to estimate from the India. Here we have some output from the spatial mapping of the groundwater storage. So we can see here the GRACE-based, GRACE and GILDAS-based GWS. The area including the India and Pakistan, Afghanistan, and Bangladesh. So here we have a very high groundwater depletion in the area, which shows very clearly in the red boxes. We can see here, and then we have some high storage recharge as well in the monsoon months as well. Like we can see September, October, and November. Afterward, we have some storage. So this is the time series variations. And here we can see the time series of the different locations for the area. This is the missing data between the GRACE and the GRACE follow-up mission. And this is the high to severe areas analyzed in the precipitation and the GWS. And this is the, here we have a GWS decreasing slowly, but it's still decreasing. The validation of GRACE-based GWS with the ground observation data. So here we have some of the GRACE-based GWS with the ground observation data. So we can see that how it's decreasing from one place to another, and how it's we can see that if we have the GWS anomaly in this direction, and we have the groundwater depth in this direction. So how now, like we were talking about the in-situ measurement. So after whenever we have some results, some analysis, so afterward we are using it for the correlation. So here we can see the correlation that we have some results, and now it have some GWS anomaly and also the groundwater depth. The validation results show the high correlation with the GWS in some areas, but in some area the results are with the R square of 0.6. So this shows that in some area we have the results are not very corrected or very connected toward the with the observation data, but in most cases the data is connected with the observation, and it's give us a 0.8 and 0.9 results R square, which is very high R square. Depth to groundwater level estimation from the GRACE-based GWS. This is basically we have used the GWR model, which is the groundwater geographically weighted regression model. That is the overall spatial mapping of water depth. So that is basically we have considered on the gray space anomaly and also some observational data. Um, we have the observation data for 4 months a year, that is January, May, August, and November. And based on the nearest neighbor and monthly GWS other months, GW depth is predicted. For the validation and testing data has been used and find that the root mean square error in the range of 3 to 4 meter. This area have a very high depth as compared to this one. Like we can see here, very high groundwater depth, and then the seasonal recharge is also there for the area. So conclusion for this case study was that the GRACE-based GWS time series hotspot analysis has been done. The spatial temporal mapping evaluated that northern India uh, is having a high groundwater storage depletion as compared to southern part of the India. Time series analysis were done for the hotspot to find that the area is decreasing with a trend of 4.4 centimeter. And the monsoon season gave a high recharge to the groundwater, which is analyzed by the spatial mapping, and the depth to groundwater level estimated using show the most of the northern area is having a high steep of water level. So that is basically we have discussed the overall measurement of the groundwater resources. Sorry for the interruption regarding the internet connection. I'm not sure. I don't know why. Currently, we have some issues here of internet. It's disconnecting again and again. But basically, if we try and if we summarize our overall talk, so we have talked about the first of all the surface water, the application of remote sensing in the surface water, and then we goes toward the ocean water, ocean and coastline water, and then after we have discussed the subsurface water as well, like here in the form of case study. So considering the overall application of remote sensing and GIS for water resource management, so it's a very important to be considered in every aspect. Like if we want to mitigate, for example, if we are talking about the flash floods or some other agriculture area for the water management, and also, for example, the watershed management and the coastal line chlorophyll fishes, and also one of the important part, which is the subsurface water. That is a very important resource for us. So that mapping and its estimation is very important. So we have overall considered the overall aspect and application to attract you guys for the utilization of remote sensing and GIS for the within the groundwater and also the surface water and also the ocean water. So this is from my side, and after now we will take some questions, and after the questions we will have some uh, practical session as well for the current study.
So if anyone has questions, just raise your hand and I will unmute you. Dr. Zishan, I don't think there are any questions for now. I think we can move on to the training.
Okay, so uh, can we have a break of 5 minutes?
Sure, sure.
Yeah, we will be back at 2:15, right?
Okay.
So we will be back at 2:15 for the practical session.
Participants, please download the file in the break that has been shared by Dr. Zishan. Dr. Zishan, you can start now if you're ready.
I hope you all have some introduction toward this interface, this software, which is ArcGIS. Today we will be, I will open some practical hand-on exercise. Basically, today we will be doing the hydrological modeling of watershed management, a case study of district Chitral. Um, I have sent the whole data set of Chitral in the image and also some small area, because uh, whenever we process the whole image, for example, if we talk about Chitral, so that taking a very long time for every specific step. So I think it's better to use the image of small area for the analysis. So I will be taking that area. Let's see, we can small area, open it, and it's better to make it to zoom in. So the better way is to right click and go toward zoom to layer. So now it shows the overall map of data elevation model of the area. We can see here. Uh, we can see here, first of all, the data elevation. This is the overall Chitral area. I will just show you the Chitral dam as well, but I just leave that because it's very big area. That is very big area, so that's why it will take a long time for a single step. So that's why I am considering the small area so that we can have some analysis and also some understanding as well. So wherever you have some issues, you can follow the steps. But if you have some issues, you can please let me know and raise your hand so that you can follow me and we can go together for the output of groundwater management, watershed management. Now, uh, this is basically the ARC2. ARC2 give us the multiple input commands which can help us to process the data. So that is the technicality, that how you can process the data step by step, because if you miss some steps, so that will be a problematic for the overall scenario. To basically remove the whole data set so that it can be easily understandable. Uh, so right now we only have the small area. So you can also open the small area image. So first step in the hand-on exercise, which is shown, is that to fill the dam, right? So first of all, we need to fill the dam. Fill the dam application of fill is that if there is some sink uh, within the data, uh, so it will be applied because we have a dam or a watershed management. So if the dam have some sink, so it will not be properly manage the water, the flow of the water. So first of all, the process is to first we need to fill the dam. If, for example, the pixel don't have a value, so by fill dam command, it will get the value by according to the nearest neighbor. Like we can see here, the profile view of the sink before and after running the fill. So we can see here, if we didn't run the fill, so that is basically the sink within the area. So after filling, considering the neighborhood, so it fill it till this one. So this is the filled sink, right? So that is very important to whenever we are using the watershed management. So that is one of the important uh, step, first step, because after the first step, we will do further analysis for that. So for the first step, it's important to know, I will be discussing every step one by one by describing the step and also by performing the step. So first of all, we need to go to the spatial analysis tool, and then we will go toward the hydrology. And within the hydrology, we have the fill. Basically, this is the fill command. So we double click it, and then we give the small area, and then click OK. So you can see it's a small area, still it's taking a long time. So if we have a complete area of Chitral, so it would be take a very long time. So that's why I have just taken a small area so that we can have the command, we can step by step apply the whole process. Okay, so now we can see here the fill command has been applied. So just to see that either the fill command have some impact on it, so we can just check on the map algebra raster calculator. So just small area will be subtract from the fill command. So we can see that where we have some areas where we have the impact of, like you can see, this is basically the area where they have filled it within the small area. So we can see here a lot of pixels areas, like you can see this, those type of fills command has been applied on the area. So that is very important, because if you don't have this fill command, so that will make basically uh, the area, the sink would be there and it cannot be used for watershed management very correctly. So after filling the command, filling the detailed elevation model, we will be trying for the flow direction. So first of all, we need to understand that what is the flow direction. So we will be applying the flow direction to show us the flow direction for every pixel. Basically, whenever we apply the flow direction, so it's basically show the flow, the smoothing way of every pixel, that how on which side of the direction would be, or for example, the pixel of direction will be shown by 8 sides. 8D method. So that is basically, as we can see here in the example. So we can see the flow direction. So this is basically either 1, 2, 4, 8, and 16, and then they have. So this is basically the flow direction is equal to the flow direction of elevation raster. So how the elevation raster has a downward flow toward one side or two sides, that is important to be shown. Now we will go to our software and just remove that one. So now we have a fill command. Fill them. So we can just remove that one. So now we have filled them. So this next step is flow direction. And the other remaining things will be like we have discussed in the here, that the 4D 8D method will be used. So same as the 8D method is used for the process, and then we can, okay. So now you can see the way bar of flow direction is going on. So you can see the direction of every pixel here. Now, as I have mentioned in the here, that you will have the multiple directions, like you can see in the map. So it is from 1, 2, 4, 8, and 16, and 32, and 64, and 128. Now you can see here that the mountainous area have a different flow. Now you can see the peak within the mountainous area, which cannot be shown if you just see the elevation, so you cannot identify. But if you find the aspect, so here you can find that, okay, this is the peak, this is one side, and this other side of mountain. This is another one, this is another one. So it is just like a mountainous area, and within that the stream is going on. So this identification is basically shown by the remote sensing data with the one step. Afterward, we will be discussing regarding the overall step for this. So we can see here that how the flow is coming toward this area, and after that we will be used flow accumulation. Flow accumulation is basically used to show that how much flow is accumulating within the every pixel. So every pixel is calculating basically going toward third pixel, and third is going toward the next pixel. So that is basically the step-by-step process for the application of the flow of water. Here we will come to the hydrology, the same special interests too, hydrology, and also the flow accumulation. And then we have the flow direction as an input. and we will have the same process, and then click OK. So you can see here the every step of the watershed is taking some time, but still it's just a start. So after that, it will take a very long time as well. So that's why we have taken some small area just to show you the example. So now here it's just a very small way, but one thing we can do is that go toward map algebra and raster calculator, and within raster calculator we will show that flow direction more than 5,000 pixels. Okay, so this will show that more than 5,000 pixels input will be identified as a stream, right? So now it will calculate the every pixel inputs, and then it will give it to us, which will might will take a little bit of. Okay, okay. So you can see here that the 5,000 have almost this one. We will be practicing some other as well, like for example 10,000, but just for the sake of stream, we can just convert it to uh, vector data so that we can have a line data, not a pixel. Those are basically the flow of pixels. So within that, uh, first of all, we will go to conversion to, and then within conversion, we will go to from raster toward the polyline. And here, raster to polyline, we will give the input as a flow 2, which is the new one, and click OK. Now you can see here, you can see here the connected streams run with one another. Now I will be practicing some, sorry, uh, like you can see here in the overall flow. Now what I will do is that I will increase the threshold that before it was 5,000. But now we will increase to, for example, 10,000. 10,000 means that the 10,000 pixel will flow toward one pixel so that it can will be called as stream. So of course that will be much more less as compared to the 5,000. So the process will be same, that we will change it to polyline. Now you can see look, you can see here you can see here that before when it was for 5,000, so it was very long. But right now for 10,000, small. So we can give, still it's a very high. So we can give it some big number so that we can have some just mainstreams can be identified that. So what we will do, we will do the same accumulation. Now we will give it to 25,000. So here we can see the most right. Now we have just a main streams. Now if we can just remove, you can see this is the 25,000. This include the 10,000, and then we have the 5,000, which shows more tertiary streams as well. So the thing is that the more pixels number of flow we giving it to the flow combination, we will have the main streams. Now we will go toward next step. We can see here we have given the applied threshold of 5,000 of flow combination, a lot of streams generated. But if we have given just 150,000 flow combination, so very few streams are generated. So now the thing is that if I can try here, for example, $100,000, and we can see how much streams are generating. This is the new one, flow accumulation 5. So we will give it as an input and get the output. So now here you can see very few streams are generated, which shows that very high number of flow accumulation in the area. Now the next step would be if you have some issues or problems, you can face them, because it's important to take you with myself as well. So kindly let me know whenever you have a question, right? Okay. So coming to after that, we have generated the slope map. So the slope basically show us that how much the degree of slope is within the area. So that is shown here, hydrology, and then after the hydrology we have some surface, and within surface we have some commands like aspect contours. So here we have a slope. So in slope we will give the input. We will give the input as a fill dam, and its input is degree in planar, and then this will be point. So now it will calculate the slope of overall area from 0 degree to 90 degree. We will have this slope within the area. So now you can see where the streams are flowing. So of course the slope is 0 to 9 degree. So within that area we have a very high streams flowing on, right? So we can see here that how the slope are generated. Here we have some diversion as well. We can see the last one is 54 to 81. So that shows that there is very steep slopes in the area, like you can see here. So that is basically the mountainous area, so which shows that the overall area has very high slopes, and also we can use the aspect. First, we will see the application of aspect. We have applied aspect command in the dam. Now, we will see the direction from 0 to 360 for all the pixel. So that will show us that in which direction basically the flow direction was the flow of the area, either it's on east side or north side or whatever. But in this, we will be seeing the direction either in south part or west part or something. So now here you can give us flow. So now you can see here the flat area -1, and the north area is from 0 to 22, sorry, 22.5 degree. And the north east is about 22, from 22 to 67, and then go on, and then from the for the most north it goes toward 337.5 to 360 degree. So that basically shows us the direction. Like we can see here the pixels, every pixel have its own, like we can see if we identify this pixel, so this pixel have north, south, direct. And if we talk about those 3 or 4 green pixels, those have the direction of southeast, and this area have a direction of northeast. So now we have some is already summed up. So we have some stream order. So for the flow direction, we can find stream order. Uh, So here we have given the input of the streams and also the flow direction, because the flow direction is very important. That is in which direction the flow is going on. So after that, it will show us which stream have how much input toward this next stream. So that is basically from the small stream to another one, and then that will call it for, like you can see here, like you can see here. Now, this is the first stream, but we have a multiple output. So this is the main stream. It's generated directly. toward 5, but this one is 3 because it's connecting with 2 more and 1. This is the best example. Basically, this is the first one, and then it's connected, two connected, and make it 2, and then goes on. Still it's 2, but the 2 and 2 more connected, so it goes toward 3. And now it's coming toward 5. So this shows that one by one, including from one stream to another, we can find the stream links, stream order that, okay, first is this one, second is this one. So those stream orders can be identified that which stream is going toward as an input toward another one. So that basically shows us that, okay, this stream is going toward this one, this stream is going to as an input to this stream, okay, and this stream overall accumulating toward the fifth stream. So basically here the fifth stream is the main stream within the area. So it shows overall input, the accumulation. And then we can make stream to feature. There are different options for that one. So there's stream basically converted to stream to feature, but we can identify it with the 1, 2, 3, 4, like we can make it on the basis of classes. Maybe you can see this is the vector data. No more raster, right? So this is one of the way for vector. So we can also add some PowerPoint, snap PowerPoint. Raster feature PowerPoint data. So this is basically the full formulation. although it's taking a very long time, I have just done that, but might be it's a mistake because sometimes it's take more than 20 minutes or sometimes it's short time. But those uh, those different stream models, the map has been shown. So we have just done some might be a mistake. Can you please update me that are you following me? I think I have made some mistake. That is basically taking a long time. So considering this one, after that we go toward a step of watershed management. Watershed map is basically based on that stream. We are basically calculating that which stream is giving how much input and how much catchment area to the another one. So that is basically the important step. I think there is some issue. It's hang. Um, Okay. Although it's still going on, so it will take a long time maybe. So we can go toward this one. You can see here the watershed map for the study area. So here we can see the overall input for every stream. Like this is basically this. Then error shows the first stream input to every watershed. So basically, they have many, and after that we have the second one, which is the green one, and then the third one is blue one. So blue basically shows that the third stream coming in, which we have conducted here, like this one. So that basically gives the input from here. And then after we have the fourth one, which is shown here as well. And the fifth one, which is the red one. And the last one, which is the sixth one, that is the pink one. So that basically shows us the main river in the Uttarakhand area, and it shows us the output of the overall scenario. After that, we will have the watershed delineation map using the PowerPoint. Like the PowerPoint, we can see we have just processed the data, but it's taking a long time. Unfortunately, I should not do that because it's taking a very long time. And the thing is that we had to do that because this is one of the important steps where we can see that if we just give it a point at the stream, so how much its catchment area will be covered within the stream. So, for example, if I am talking about this stream, so that much, this stream is covering that much watershed area within that, right? And now we have some second one, this one, this one. So this one basically considering the whole area because that is the main input toward the whole area. So that you can see here that the pink color is showing that all the input from the whole Chitral district is coming toward this outlet. So that outlet is basically covering the whole Chitral area. So whenever we cover the watershed on this outlet, it covers the whole Chitral area. That wherever the will, precipitation happen anywhere, so that will cover and the outlet will be in this specific area where we have the high flow of the water. That is still going on. So if you have some question, please let me know, and we will be doing the session till few minutes, and we can do some other analysis as well if you guys want.
Dr. Zishan, your voice is breaking up a little bit.
I'm just asking that basically this snap PowerPoint, that process is taking a long time. Although I have taken a small area, but still it's taking a long time. So I think it's the participants are following, and if they face some issues, so I will be happy to address the issues. I hope it will be done by that time. so that we can further one more step is remaining, which we talk about it, like the catchment area. So after the PowerPoint, so we will have the catchment area like that one we discussed already. So this is basically one of the small stream we have taken. So we can see here the catchment area of this stream. And the second PowerPoint we have taken outlet at this point, where we can see the whole Chitral is coming under this way, and it's covering the whole way. So any participant which is following and have some trouble in the data or in the software, so please question and I will be happy to answer it.
So anyone with questions, just raise your hand and I will unmute you. Please participate because this is the last day of the training. So if you have any questions regarding the hands-on training, do ask Dr.
Yeah,
Zishan now, so he can ask you.
any question regarding the GIS and remote sensing and any application questions are
Yeah,
more than welcome.
feel free to ask Dr. Zishan so he can answer them.
We will be ending this session within next 15 minutes. So if you have some question, and I hope,
There is one question in the chat.
yes, please.
It says, sir, if we want to run these hydrological modeling, the only data I need is DEM of the study, right?
Yeah. Currently, at the moment, if you want to do the watershed management, so at the moment you only need SRTM depth. But with the passage of time, whenever we are using some, for example, the discharge data and calculating some water modeling, so then we need some other parameter as well. For example, the discharge data of the gauges data and some other data for streams as well. So for the current, just for the stream flow and hydrological modeling, we only need a digital elevation model, and that it's better to use the SRTM model. So it will be easy for the processing.
We have another question. It says, will the same method apply for groundwater in deserts?
Uh, no, that is basically for the surface water. For the groundwater, as I have mentioned in the my presentation as well. So if I talk about the GRACE data, uh, that is basically used for the groundwater. So that is basically available at the Center for Space Research and NASA Jet Propulsion Laboratory, and also the another one that is the German Research Center for Geosciences. So here we have the data set, and then it have completely a different step of analysis. It can be used by ArcGIS, and also the MATLAB will be using. So that is for the groundwater, it's completely a change process. The current one is for the surface hydrological model. It's taking hello. So this the manual which I have shared, it will be helpful for you guys to utilize the data elevation model data, and the DEM I have provided it to you. Even you can test it on small data. Like you can see here that I have just, even on a small area, it's taking some steps are taking very long time. So that is some issues that you need to sit by yourself and step by step go on. You are welcome anytime, not only for the training, but later on you can uh, email me or somehow you can access me. So I hope I can help you anytime.
There is one more question in the chat, if you want to take it.
Uh, for the subsurface formations and cross sections, um, I don't think so. For basically the remote sensing data, mostly it's working on the surface of the Earth. So considering the surface of the Earth, we are explaining or we are expecting that the same situation would be the subsurface as well. So at that point, it cannot be mentioned that we cannot do this process only by using remote sensing, but it can be helpful by using. Mostly people are doing the lithological formations of geological data. So that can be done, but that is also the somehow steps are taken. But yes, it can be done at some steps. But still we need to do the either a field work or either some other modification as well. But yes, lithological formations are doing by remote sensing data. I have shared my email ID. So if someone want to work on it, and any type of remote sensing or GIS question and applications are more than welcome for the next few steps. Uh, just for the sake of information, after that, this PowerPoint, we can put a point anywhere and it will show us the watershed of that specific area. So that is basically the process for this one. Like if we click here at that point, so it will show us the watershed of the catchment area of that specific area. So that is basically the utilization of this PowerPoint area. If someone have done that, so you can share your screen, or you can share your screenshot of the chat as well. Or if someone even stuck there, so he or she can share screen, and then we can. I hope we can help. or help her. I have just ended the process, close the ArcGIS and then reopen it just to show you some other steps so that we can then end the session because it's important to show some other steps. But although you guys have time, so it's better to complete that PowerPoint, so it will be easy for the watershed management. Now you can see the watershed management from different streams, that how it's giving input from one stream to another one, and then how it's changing from one place to another one. That is one of the main steps. And then we can try different steps because every step has its own uh, function, like stream link and stream orders we have done, stream link we have done this in the PowerPoint, although I wanted to do that, but it's taking a very long time. So that's why we couldn't finish it. Watershed we have done. So after that, the surface, in surface we have done the aspects and also the slope, and we can do the hillshade, curvature towards contours, and also the view shade. So those type of multiple hydrological parameters can be applicable for the using the digital elevation model with the help of RTLs. That is the overall step and overall process for the hydrological modeling. Thank you so much for your cooperation. And once again, I'm sorry about the internet connections. I don't know here it have some issues regarding internet in the university. So might be there is some problem just because of disconnections. So I think it's time to end the
Thank you so
session.
much, Dr. Zishan. Let's see if we have any last question or not. Um, Questions, please mention in the chat or raise your hand. Okay, Islamic University in Uganda. Do we have Professor Ismail here for the closing remarks, or we have 10 minutes till he will be here?
Yeah. So we can end the session, and then after 3:40 we will have the closing remarks, right?
Yeah, so I'm just going to wait now for. I'm not sure, is Dr. Shafiq going to join us for the closing?
Yes, he will, I think, join us on 3:40.
3:40.
So we will
I think
uh, we have to we have to end the session at 3:30 so that I think everyone can join us on 3:40.
that is fine. I think we have, I think, 5-6 minutes. So if you would like to just recap for today until we can
Okay.
start the closing session. So just,
Yeah, sure.
I think that would be great.
Okay. So today, although we have some issues regarding the internet, but still I will just overall talk about management and monitoring of groundwater and also the surface water and also the ocean and its application using the remote sensing and GIS data. So I think uh, there are multiple sources of data set. Even if you want to do some research and some work on the groundwater or the surface water, so we can do a lot of, we have a lot of stuff regarding the remote sensing data. which can be processed, and also we can have some meaningful result from that one. So in that case, if we talk about the surface water, so for the surface water, we have used hydrological modeling, which we have done a little bit in the exercise session as well. The second one is regarding if we talk about the surface land use data, so how the surface modeling can be compared with the land use and land cover mapping, so that we can see the impact of the surface water and also utilization for the agriculture, also for the residential and industrial zones. So that those type of applications are very important and very considerable for the future perspective. And another thing is regarding the main resource, which I feel is that considering the some Pakistan case and India case study, so the main resource which we are going to be end very soon maybe, but the thing is that we are utilizing the groundwater much more as compared to its recharge. So uh, this recharge and this overall groundwater utilization is very important, need to be mitigated and also need to be monitored for the time period. So if we monitor it and also if we mitigate its reduce the utilization of groundwater, so it will be helpful for the next generation, because currently if we use it much more, because that is limited resource. So if we use it without any monitoring, so it will be at one day it will be finished. So that is a big problem and that is a big challenge for the current era, for the policymakers and also for the researchers to think about it, that how we can reduce the groundwater usage, and also the due to climate change, the glaciers are melting. So that is also one of the resource which we can utilize it with the passage of time, but it's just going on and toward the ocean. So those type of applications are, I think, everywhere. Those type of challenges are there for the groundwater, or either for the even the glacier melting. Climatic change is worldwide. Global warming is worldwide. So those issues should be identified and recognized by the policymakers, that how we can reduce its impact on the livelihood. So the third part is regarding the ocean or the coastline area. So that is one of the important factor, that how we can reduce the ocean water, how we can monitor and how we can make a helpful for the even the, if we talk about the chlorophyll A concentration mapping, or even the fisheries mapping, or some temperature, sea surface temperature. So those type of applications are very important. And for those applications, we have a free data source which can be used by different researchers for the different purposes, like sea surface temperature, anomalies, and also the other layer like land cover for the groundwater, and some chlorophyll concentration can be identified by MODIS, and some other applications are also identified by multiple research papers. So those type of applications and those type of work has been done by multiple uh, researchers. But the thing is that how we can utilize, or how we can get this knowledge to use it in our own community, either it's in our own country or either it's in neighboring, so that it can helpful for some community. For example, if I can say that, okay, China have this model or US have this model, but that model, if I can apply it in my own country and it help the
community. So then we can say that, okay, I have taken the help from that researcher and I applied that in my country and it helped the community and it was worthful. So that is important, that if you have some research, the policymakers should utilize that research and then it will be further helpful for the community for the utilization of it. So that's it from my side.
Thank you so much, Dr. Zishan. So we have Dr. Shafiq here with us. So I would request him to give some remarks towards the closing. It has been a 2-week long training, so he can just recap it a bit and give his final remarks. Over to you, Dr. Shafiq. You can unmute yourself. Yes, Dr. Shafiq, if you can hear me. I think Dr. Shafiq is traveling, so there must be some signal issue. Is it?
Okay, do you hear me now?
Yes, it's clear.
Yes.
Okay, thank you very much. Thank you for the invitation. I'm again grateful to the Comstech University of Islamic University of Uganda and other colleagues for organizing this training. I'm also grateful to the rector, Professor Ismail, for arranging this training and collaborating with the participants and calling out good faculty members who were very interested in the workshop. We had arranged this workshop with considering that it will be a basic training initially. So we try to give you the basic flavors of how GIS and remote works. And then we also have shared few of the applications, like how we can use the GIS and remote sensing and space technology for the forest mapping, how you can use that for the mapping the forest species and carbon stock analysis. Then we had focused also on the applications of space sciences uh, for the geohazard, mainly the floods, landslides, and today we had another important talk on the water resources. So we have tried to cover the wide range of application of space technologies and light accessories, the light tools. We hope that the participant got the basic knowledge and basic ideas. Um, from now onward, we expect that the participant should follow it up. It cannot teach everything within 2 weeks. It's a long process. If you got the basic knowledge, you know the basic terminologies, you have the basic ideas. Now you can search for the internet. You get a lot of information from the YouTube, from the Google. There are a lot of literature available. You can make use of that, and some software are available. I presume now every one of you has a system. Everyone of you has software installed on your systems, so you can make use of that. We have also shared some data, some tutorials, so you can also work on that. Uh, I mean, beyond that, if you still need some help, my email is there. Dr. Sami email is already there. Our resource person are there. They can help you with that. But we expect, I would like to request Dr. Professor Ismail that we expect that we should follow it up. We should not stop here. This was the basic training, but now we should think about developing some joint projects, developing some joint studies where we can do that with your faculty and also with the students. With this, I would like to thank again to the Comstech, to all the participants for your active participation. We enjoyed a lot. There were a lot of learning also for us. I'm also thankful to the resource person, especially Dr. Samiullah, Benazir Iqbal, Ishfaq, Dr. Krishan, and all the resource person who has spared their time, who has shared the knowledge, and we expect that the participants have got the basic knowledge. So with this, I would like to thank again participant, IIU, and Comstech. Thank you very much.
Thank you so much, Dr. Shafiq. Let me see if we have Professor Ismail from Uganda with us or not. Okay, so we were expecting Rector Islamic University in Uganda for some closing remarks, but I don't think they are available right now because they also have an event going on in Uganda. So as from Comstech, so this marks the end of the 2-week training on GIS and remote sensing. And on remote sensing. And on behalf of Comstech, I would like to thank once again our resource persons, especially Dr. Shafiq and Dr. Samiullah, for taking out such a large chunk of their time out of their busy schedules, and they have given us such informative and interactive sessions. And a special thanks to the rest of the team, which had Ms. Benazir, Ms. Ishfaq, and Dr. Zisha. And also to all the participants that have joined us from across the OIC. We have had a good number of participation also from the Islamic University in Uganda, and for that we are also thankful. Some participants were asking about the e-certificates. We'll issue you the e-certificates around 7 to 10 working days after today, and they will be emailed to you. We'll have a look at the logs, and for those that have had complete participation, we will issue the e-certificates. In the end, I would just like to say that it was a brilliant virtual training session, and hopefully in the future that we can transform this into physical events in the future. So thank you very much once again, Dr. Shafiq and Dr. Sami, for this wonderful training session. And that is it from our end. And we will end the training session on these remarks. Also, finally, all of these lectures that have taken place, they're all recorded and they are all available on the Comstech YouTube channel. So if anyone wants to go over them again, you can easily visit them. And as far as the presentations go, I would request Dr. Shafiq and Dr. Sami to forward all the presentations and all the data that they think should be shared. We'll compile it all together and share it with all the participants. So thank you so much once again, and bye-bye.